Good afternoon, everyone.
Hey, is that Jason?
Yes, it is.
It is.
Gosh.
Howdy, everyone.
Hi, John.
Hi, good afternoon.
Hi, Gaurav. Good afternoon. Let's give another minute or so for folks to connect.
We should be meeting at the beach on a day
That's,
like this, man. I hate sitting inside.
yeah, that sounds lovely.
Sounds like a perfect day for volleyball to me.
All right, it looks like Oscar's joined. I think we've got most folks that we're expecting. Hopefully, a few more will join. As Bill reported last week, he's on vacation for the next 3 weeks. So Oscar and I will try to keep us moving forward so we can make progress. Today I'll ask if anybody's got any concerns with the minutes from last week. Then we will talk about scheduling the Open XLA presentation. We have a topic on the accelerator first versus device first architecture, and then we'll kind of continue with one MCC, the discussion we had last week. After that, other topics folks were hoping would be on the agenda.
No, the only thing is that you guys asked me to reach out to Renwu
Yes,
regarding the type 2 versus type 3. And
yes,
Jason, you're on the copy on that one. So
I am perfect, and will put him down for next week to present, and yeah, we appreciate that. Thank you.
Yeah,
sure.
thanks. Okay.
All right, does anyone have concerns about the minutes that were posted from last week?
All good.
All right, good. All right, so then next topic, Gaurav knows somebody in his organization that would be able to speak about OpenXLA. The problem is that person is in India. So we would need to find a different time for a one-off meeting. Without necessarily starting a doodle poll, which we can certainly do for that. I was just wondering if we could set something up like, well, it's probably going to need to be like 6 p.m. maybe at the earliest, if we wanted to do it in the evening, or maybe we could do something, as early as, well, probably just to be respectful of their time, probably not a whole lot later than 8 p.m. Pacific time.
Yes.
Because that would be 9:30 p.m. or 8:30 p.m. and
I think that
India.
part is okay. 9-10 p.m. India time is fine. I can speak for that, but I think we have to consider the folks who join in the Europe time. For example, John, as an example, or I don't know, John, what time zone are you at?
Usually I'm Central, but right now I'm Pacific, so no concerns
Oh, I
there.
see.
I
Okay.
think there was someone from the Netherlands, I think.
Yeah. So I think the reality is it's extremely difficult to find a time zone that's going to work for all three of those geographies. We're probably going to have to, for the European folks, we're going to have to rely on the recording for them.
So in that
Unfortunately.
So what I'm
case,
saying is that Pacific mornings will be okay, should be okay, right?
I think if we have Korea participants, I don't know if anybody is from Korea in this team, but if we have Korea participants, then I think after 4 p.m. also works here. So another possible slot is like we do something like 4:30 or 5 Pacific, which will be what
So
India
5 Pacific
is.
would be 5:30 a.m. in India.
No,
I
no,
don't know.
6:30.
6:30?
Are we spring forwarded? Yes, we are. So
Yes, we
yes, it
are.
will be. Yeah. Yeah. So maybe. Yeah.
So I don't know if
I'll
that's
let you
the
guys figure
potential.
it out. Yeah.
No, but
I'm looking at I'm working at
is
the
there
time
any,
converter. Go ahead.
but sorry, is there any participant from Korea?
There is one. Hojin.
Hojin is in Korea. Seung-jun, are you in Korea? Where are you?
Actually, I'm in San Jose.
Okay. And you're with Samsung, by the way?
Yeah, Hojin in Korea.
Okay. So it sounds like morning would be best. Morning US time. Or sorry, other way around. Evening
Yeah.
US time, morning in
Like
India
an
would be
8
best.
p.m., we all kind of grab dinner and then sit down, and then everybody else, it will work out. Okay. Pacific people can kind of get in
so
just after dinner. Yeah.
So 8 p.m. would be 10 p.m. for John. I don't know if John
Okay,
is willing to
that's
go that quite late under normal circumstances or not.
Well, like I said, for the time being, I'm Pacific, so 8 p.m. is fine.
So like when you say time being, like for the rest of this week, or are we talking, we're probably talking next week at the earliest before we could set this up.
Yeah, it'll be a few weeks.
Oh, okay. Okay. Okay, great. Then that probably is maybe the right answer. We can target a 7 or 8 p.m. Pacific time.
Well, maybe you can ask Gaurav, is this week possible?
Or is that too short a notice?
Yeah, I think this week would be too short. We should
Okay.
plan something next week.
So what if we well, we already have a presenter next Tuesday during our usual time slot from Intel. So we can either have two meetings next week, one during our regular time slot, and then maybe another meeting in the evening, or we can shift our meeting on the 24th to have an evening time slot. What's the preference?
Since this is a one-off, at least for
It's a
me.
one-off, yeah.
Yeah, we can have an additional meeting next week. That's my thinking.
same here.
Anyone opposed to that? Okay. All right, then so Gaurav, do you want to ask your contact about presenting, 7 or 8 p.m. Pacific time next Tuesday?
Yes, I will go back and confirm.
Okay. Okay. All right, fantastic.
Yeah, thank you, Gaurav.
Thank you, Gaurav. Yeah, that's wonderful.
Thank you.
All right, so the next topic is accelerator first versus device first. And Pankaj, thank you for agreeing to kind of lead this discussion.
No problem. I welcome the opportunity. So we talked about this, and I thought I'll just put a little bit of meat behind the bones. I'm supposed to be interactive with only 2-3 slides. Okay, and right away to give you somewhat concretely what I think when I think of device first versus accelerator first architecture, especially for a team like this, which focuses on interfaces and protocols. In a device first architecture, you have a traditional setup with some acceleration of mainly capacity oriented functions through a transparent internal accelerator. It's slightly configured through a control interface, but the bulk of your protocol is just standard load store traffic to memory. Okay, so it's commonly used, like if this was NVMe, this architecture would be the CST architecture from SNIA and NVMe technical group, which was used in pre-CXL SSDs or NVMe transport with a new command set. And IT Nexus terminated at SSD controller. Accelerator commands were reissued to embedded or discrete accelerator. And there is some possibility that there is some DMA leverage built into the internal accelerator. So even though commands might be getting picked up like through a shadow address space in case of load store protocol, okay, that's commonly used for memory compression, that if you're doing transparent access to a compressed area, then the internal accelerator will pick that up, do inline decompression, for example, and deliver those bits. But even though the function might be getting invoked through an indirect path, the data flows as normal. And so we'll talk about what is easy or difficult about these, but largely the idea is, you might, if this was, for example, a transparent compression accelerator, then you might have some additional configuration to come in and define which kind of compression you want to use, what will be the size of the compression windows, and maybe even program a custom dictionary, okay? And it's possible in this kind of accelerators, as was in the case of the CSD specification, that some working memory may be exposed. And operators are either hardwired or pre-installed and are enumerable, like you can enumerate whether that acceleration is present or not. And the idea of these accelerators is that because this is your primary traffic pattern, which is data access pattern, so the presence of the accelerator should not overburden the common use case, which is in case of memory load store access, or in case of storage NVMe read write commands. Okay. So if presence of accelerator interferes with that, that is seen as a bad thing in these architectures. Okay. In accelerator first architectures, you are in an environment where domain specific acceleration is needed. This might be like prototypical use case will be machine learning. So you're going to invoke a lot of functions on an accelerator. And occasionally, you're going to either collect results or supply parameters or do some load store access. But that's not your primary interface to the memory, which now is behind the accelerator in this architecture. Okay? So in this first architecture, accelerator is behind the memory. In the second architecture, memory is behind the accelerator. Okay. And so one of the things that people care about a lot when they build this kind of accelerators is they worry about a lot of pipelining and coherence. So they don't like pipeline bubbles between the host, what is running on the host and what's running on the accelerator. They use a lot of memory to memory transports, such as CXL and UA link. That's where these architectures are coming up. And storage or memory is tucked behind accelerator's memory. So you won't even see it as storage, for example, here. And then, there is some shared virtual address space, because for ease and flexibility of scheduling function and data between these two, you generally operate in the context of a shared virtual address space. It might not be tightest possible coherence, but there is some alignment on virtual addresses to keep the overhead of data and function low over here. Okay, and there's a lot of soft function that moves around in this kind of architecture. Here, it tends to be more of kind of well-defined hardened functions. Okay. The reason why these things exist as two separate architectures or recognizable architectures is because actually they represent slightly different market segments. So the first architecture with, a lot of transparent acceleration that is generally operating on physically addressed bits, like compression, encryption oriented acceleration are common use cases. These are capacity oriented use cases. Whereas the use cases you see in the accelerator first architecture tend to be performance use cases. They might be offloads coming from already very, very fast compute. And so when that gets offloaded, there is a requirement to be in a very high performance architecture. And you're therefore working with, like I said, very pipeline, virtually addressed computational memory. And so, the use cases for these accelerator first components, they originate on the left side of this workload field categories that we have identified, like HPC ML and in-memory and vector databases. As you get to some of the use cases that are more capacity oriented, like storage services or large in-memory caches behind Redis or such, and even some of the sort of bulk offload use cases like sort and shuffle offloads and MapReduce, they can live in either kind of world. And so there is a transition. This is not hard boundary, but there's a transition on the right in this kind of workloads to wanting physically addressed and transparent acceleration as you come over here requiring programmable and pipelined acceleration. Okay, so the characteristics of these and what makes one or the other better or difficult are quite interesting. So we'll start with the right side of the picture first. The inline internal acceleration is needed because you don't want that the memory characteristic to be hidden because of the presence of the accelerator. You don't want the characteristic to be altered. You just want to see some benefit like large capacity or additional protection or like in the form of decryption or so on. So large capacity might be through compression and decompression that is inline and transparent. So the most difficult aspect of designing these accelerators is to keep them line rate. And at the same time, because you are a slight overhead on top of what is otherwise a memory device or storage device, you cannot impose too much of a cost or too much cost in terms of power. And these requirements taken together become really complex in the case of maintaining full line rate. And as you know, whether it is, PCI Gen 4, now, going from PCI 4 to 5 to 6 very rapidly in case of SSDs. And in case of memories, the same PCI line rate curve drives some of the CXL generations. So the adoption of new SerDes is very, very rapid, and therefore developing components where you can, continue to use like 1 million LUTs of FPGA or use small area logic in a low cost process. That is extremely challenging in case of these accelerators that are hidden and in physical address space. Otherwise, the other aspects of them are less challenging because they're not generally soft programmed. So, you can define a few IPs or have some fixed IPs in things like controller ASICs, and the functions, they will generally tend to operate on the bits. So they tend to work also with things like sharding or what do you call interleaving, right? So these functions are a little bit, this type of acceleration is a little bit better for that. Okay. Now, here, you're in a semantically rich, virtually addressed environment, but because you're talking to an accelerator and your primary concern is to speed match something else that is going on, you have some flexibility in what you can place here. Now that flexibility comes at a cost of building a good optimizer. So, you don't end up placing function or data in the accelerator domain in such a way that pipeline bubbles form. Okay, so because of that flexibility, the software needs to be a lot more mature and uses, either like in case of database, it will use some sort of a cost model for the query or query fragment to schedule a portion of the query plan on the device, for example. Or in case of a multi-threaded, multi-step task, it may decide, hey, I want to offload some layers of a deep neural network to the device. Okay. Or maybe at a coarser level, allow the device to compute on embeddings and the rest of the network to compute on the higher level layer logic. So these are designed to meet a lot of unique characteristics of functions and memory that can be on devices. So they deliver, while they are not transparent, they're good match for new memories like TIMs that compute and are programmed at a higher level. And you also, try to, because these are things that are working at a very high rate, you try to keep the coordination overheads very low by not having a protocol that requires too much rigid data movement, like eager movement of data for feeding or invoking a function and collecting result. Instead, you have a more of an on-demand regimen with coherence or low coordination sharing. You know, that's the architecture. So here the fact is that most storage and memory standards do not have a natural architecture for function invocation. So you have to invent that. That is the most difficult part of this kind of design. Whereas over here, the most difficult part of the design is to build some acceleration function that will become completely transparent in terms of protocol and performance to a very traditional view of load store or NVMe. Okay, so those are the things that I know of. I just wanted to, make a few slides, share with you on, what these are and which ones we might want to adopt and do APIs for in our work here. That's all I have today.
Hey, Pankaj, this is very good. Do you have real-world examples of
Yeah.
these, devices with these architectures?
Yes. In fact, the only reason I know this is because some of the devices we engineered went from one architecture to another, and the functions that we were looking at in those devices were things like search-oriented functions, like regular expression searches, or compression-oriented functions for both block-oriented and page-oriented compression, but also database compression. And then also some specific like format-oriented packing and compression, like Parquet, encode, decode using line rate. What do you call them? Oscar will help me out here. But you take long strings of bit and you run length encode or decode them to make Parquet compression. So a variety of engines were built, for example, for Smart SSD in my experience at Samsung. And later I worked on compression engines. And generally, if you're doing something like transparent compression for memory, you try to be in this architecture. When you're building an accelerator for machine learning or database, you are generally in this kind of architecture on the left side.
Okay, in other words, would you be able to provide some pointers so that for reference. So we can.
I think the white paper
those
already
further?
has them, Oscar. The white paper
Okay.
that our group did. Yeah.
Okay. Thanks.
I just didn't present those in this form, but I'm building upon what we covered in this group's white paper. For example, the use case families are well documented in the white paper as it exists. And there are some additional use cases that are unique to tiered systems. So for example, if you have internal tiering in the devices, and you sometimes can have use cases that can be in all of these areas that are related to demotion. So generally in a performance tier, you are not in a compressed format, whereas in the capacity tier, you might be in a compressed format. So demotion may cause a compression use case. Generally, in a disaggregation situation where one of your capacity tiers is disaggregated memory because there are tighter requirements on encryption when memory leaves the CPU and OS protection. So there may likewise be the need for encrypt on demote and decrypt on promote. And there may be internal use cases related to tiering also that do not have to do with any of the workloads, but uh, uh, like hotness, coldness monitoring, or other kind of control plane use cases. There may be function backcalling. So you find that in older papers on compressed memory, especially when it was done inside the memory hierarchy of a CPU. You found that when, for example, they were promoting from a compressed L3 to an uncompressed L2, one of the things they were doing was rather than engineer a processor into the SRAM of caches, they engineered such processing near those SRAM tiers. And they invoked CPU function, which had visibility into both tiers to do the conversion. Okay, so there are additional use cases that are not workload related, but rather purely from consideration of having a performance tier and a capacity tier that are also possible. And depending on the orientation of those use cases, whether they're capacity-oriented use cases or performance-oriented use cases, you will follow one or the other architecture for your accelerator. Okay, but I wanted to point out to you that in the age of increasing line rates, I mean, that's the surest thing in our industry is that line rates are improving very rapidly. Building these transparent accelerators on the cheap and keeping wattage low has become extremely difficult. So generally, what I've seen over the years is that the trend in acceleration is a capacity reducing trend, like filtering and searching use cases dominate. So if you remember, tables that we prepared for these use cases, a lot of use cases were data reduction oriented use cases, which is can I filter, search, or do inner products to identify just a top K or just the few pieces of data I need to pull out. Okay, so that consideration now tends to, that consideration now tends to dominate computational memory use cases. I've seen a lot more of use cases that will match this architecture rather than that architecture.
So where are those computational memory products that you're referring to that you are seeing a lot of that?
I mean, Gaurav, you're asking me, I'm sure, to promote some discussion, but you know the answers as well as I do. That
No, seriously. I mean,
computational
Marvell has
memory.
one, right?
I mean, in the absence of standard ways of building computational memory, okay, the most of the technology for computational memory exists in prototypes at universities and in places like SK Hynix, CMS, or Samsung various devices with the C suffix, right? So I don't know what else to tell you.
No, that's fine. I mean, that's precisely what my understanding is as well.
But,
Okay.
I would answer one more way, which is in the absence of memory or storage devices with compute, we are seeing accelerators with memory as the most practical use case for this first family. And as we have learned from Microsoft's splitwise team, that one of the things that is taking the place of accelerator with memory is old GPUs, where the compute is not considered fast enough, uh, like a Hopper compute or a Ampere compute will not be considered as fast as Blackwell compute. But so those old GPUs are being used as primary a place to hold things like KV cache and do a memory intensive tasks on them, like Splitwise team was doing, rather than compute intensive tasks. And they will deploy new GPUs like Blackwells for the compute intensive tasks like prefill. So,
Right. Basically, the disaggregated compute architecture, right?
yeah, but
Exactly.
I'm saying that in our world, right? Look at the team we are sitting in. So in the context of the DCC and CXP teams, the uh, the things we tend to look at are those that have uh, a substantial number of bits that are being covered by the accelerator, right? So in that sense, a lot of what is out there and taking the offload today is more amenable to accelerator first architecture.
So one more thing, right? I think worth considering is the data movement capability in terms of bandwidth. So basically what you stated, right? Accelerator and memory in terms of capacity versus performance. But one another very crucial aspect is the pipe into these devices, right?
Yeah.
Because I mean, if you were to take, let's say, that Microsoft splitwise scenario, I mean, that use case is a very big one. So it's very important, I mean, to have high bandwidth, right? Because when you attach these devices to AI accelerators, then the amount of data that needs to be moved is, it requires high bandwidth too, right?
Yeah. I mean, I think within the scope of DCC, because the per lane bandwidth is following the industry curves of adoption. So then, the main difference, Gaurav, in the flavor of what you are trying to discuss would be the widths, right? So generally speaking, one might say that there is a by 4 versus by 8 or 16 kind of difference. Okay. I know I'm trying to take something broad that you were saying and turn it into a narrow statement. Okay. But that's how I see it. I think over time, even other differences might emerge. Okay. Like something is, on a very, very slow, separate kind of physical wiring, then something is on a very high speed physical wiring. But generally, the scope that we tend to cover, it's very common to have some kind of a PCI Phi based interconnect. And then, the differences are in protocols that you're carrying. And so maybe those will diverge a little bit more in the future. But so far, I think the main difference you see is in the width.
So would you consider, memory fabrics, which is memory fabric for AI, which is under discussion, to be um, aligned with this? I mean, these accelerator architectures be aligned with memory fabric for AI, or that's different?
I think we are mainly our focus here is on memory and storage devices. And so that's for all workloads, including AI workloads. This is a broader discussion, Gaurav. Okay. So yes, definitely, vector DBs and ML training and uh, inference use cases are on the left side of the picture, right? And they drive a lot of these uh, performance-oriented use cases over here. Okay, so AI is notorious for being very demanding in terms of performance, um, but it puts pressure that starts on the left here, percolates all the way down, and you can see some of the influences that AI has had on things like storage services, where you went from normal NVMe to GDS and then GIDS. So, the pressure keeps rising to do more over here. Now, we haven't seen particular pressure on computational storage from AI, but some of the search use cases that are on very, very big data, including some vector database use cases. If you look at Kioxia's Isaac as a prototypical example, okay, it's showing up all the way over here as well. So the use cases, because if the central compute engine is over on the left side running these use cases, the pipeline that feeds the AI use case goes all the way back to here, because you're still having to search and find documents, turn them into embeddings, find the top K embeddings to match a prompt, and then do that in the vector database and then feed to the inference engine. So even AI, this is why I don't write AI, because it's too broad a word. But I hope I answer your question, Gaurav.
You did that. I mean, it was simple that yes, I mean, you do consider this applicable to memory fabrics for AI. I just have a doubt based on a statement you made, just that you consider PCI PHY-based interface, whereas memory fabric for AI demands much higher bandwidth, as you know. I mean, for the scale-up domain, and we are
Yeah,
already considering bridging between, scale-up and scale-out domain as well. So
right.
those are all very high bandwidth
Yeah.
scenarios.
And I think, generally speaking, the interface that we are talking about here is not looking to penetrate the scale-up domain, right? So it lives at the boundary where scale-ups are either scaling out or disaggregating, and that's where this stuff lives. So its scope, I think, is the same scope that uh, DCC team defines, and then also the CXP team, which is it's the scope of like computational device memory and storage devices like memory modules and NVMe SSDs with or without compute, and then uh, and then same thing with memory modules, right? That uh, either computational or non-computational flavors. Um, and
Exactly. So when you consider, like, let's say high bandwidth memory be um, available
that's
as a
above all
service.
this, right, Gaurav?
Sorry?
I mean, it's the big fat compute and access engine that's looking to just take in the data and compute. So your normal GPUs with HBM or GPU scale-up clusters with HBM will be sitting over here in the top tier. That's not the scope at which we are considering these APIs that we are trying to design, the offload APIs, right?
I see.
Yeah. So the thing is that the main thing to note from your comments is that just because where that market is and what it tends to use, right? And because that market is over here, okay? So its architecture bleeds into the use cases over here, the performance use cases. Okay. And
No,
it,
the use case I mean, one of the use case that I touched upon was increasing the high bandwidth memory capacity.
right, Gaurav, but if you increase that capacity across the kind of interfaces that we are considering in DCC work or CXP work, okay, that there is some disaggregated memory or computational disaggregated memory that is sitting right next to a GPU with or GPU cluster with that scale-up architecture that you just described with HBM, okay? The characteristics of that architecture are bleeding into the use cases over here. Okay. And the way that that works out is that, I'm sorry, let me look at this diagram over here, right? That there's those use cases like training and inference, they will either be in a compute only architecture, or as they start to look at more capacity orientation, they start to demand some acceleration near memory that is in the same style as they do their work. So the software architecture, considering that there will be some very high thread count software that will be running on CPUs or GPUs over here, that then demands an architecture that is accordingly high performance pipeline multi-threaded from the accelerator that wants to offload that. Whereas the use cases that start from primarily data access side, they are very comfortable not having a computational metaphor driving things, but more a capacity conversation, for example. And so there, you're looking for, hey, I don't want to spoil my characteristic. I want to just deliver added value through encryption or compression, being the prototypical use cases there. Okay, so that's the kind of world that we live in, and those are the words that lead to these two architectures. And I think in designing APIs and protocols, you have to think about, how do you accommodate the considerations. Actually, the wrong architecture applied to the wrong use case can give you a lot of trouble. So, you may end up once you put memory behind something, okay, it's kind of easy to do in a PowerPoint diagram, but architecturally doing something like this has consequences. They could have consequences for things like read or write bandwidth or read or write latency, for example. The fact that even a tiny portion of the accelerator sitting in the access path of memory can actually affect the characteristics that you will see in the load store. So if load store is your primary data path and you're absolutely looking to leave it pristine, you're better off in this architecture with transparent acceleration. But then your challenge is that meeting these characteristics, which are expected from that kind of a device, is extremely challenging. And there are limits on how much value you can claim if you are not primarily a programmable accelerator. If you're primarily a programmable accelerator, the chances that you will meet the cost characteristics of primarily load stored memory are very poor. So here, your architecture is mainly an architecture of value where the memory that you're holding might not be the cheapest memory, but the fact that it has near data processing is the source of all your benefit. And so exercising that under a careful cost optimization becomes the focus of your attention there.
Pankaj, following up on excellent explanation you gave. So the device first is command driven mostly and can be highly standardized to run specific operations, whereas the accelerator first may have, like you said earlier, a very custom interface to make that function invocation happen. But in our previous meetings, you did show the desire to go to the accelerator first.
Yes.
And for our DCC, is that something you suggest that we should look into more?
I think so.
And can some of
Yeah.
that be hidden by the API? That was kind of my question.
Yes, actually good questions, both really good questions, because I mean, the thing is that there are pros and cons of these architectures, right, Oscar?
Right.
And I think not hiding, for example, comes with software consequences. So what you guys are asking is, can we combine the best of both worlds? And if I had more time to prepare, actually, that is the direction in which I was trying to do or planning to do some additional work, is can we have our cake and eat it too? Right?
That's exactly what we want, always.
Yes, all the time. I know everybody wants that, right? So I think the short answer to your question is open formats. Okay. Right from the first day that after we finished our white paper and all the learnings we had in the CXP team, and then started to engage with you guys, one of the hopes I have had is that the learnings from the CXP white paper in the area of open formats can be used to combine the best of both worlds. So maybe there is a new architecture that, what we like, one way to follow up on this, Oscar, would be to look at the most difficult aspects of these two and to combine them with the advantages of the other. Okay, to solve, for example, the function invocation problem with the hardened logic architecture of this guy, and to take the line rate problem and to combine that with some of the programmability benefits of this guy.
Right. That
Okay.
sounds fascinating. Yeah.
Okay. So I do not have, a fully well-developed answer, but I suspect that by scope limiting to open formats for data and compute, we can address a very large chunk of our market segments by a best of breed architecture that extend some of the virtual addressability into this domain, for example, on the right side, and addresses some of the fixed function architecture and its discovery and implementation benefits to this left side. Okay, and it may be that that's a ticket to a best of breed architecture. And I encourage you to either co-author the next few slides with me or do your own. I very much like your question. And
no, definitely. I mean, Jason and I were discussing on the side that we can make this a chapter on why we're going in this direction, right? So I think there's a lot of value add we can do towards a specification.
Yeah. And I think, this, for example, can motivate, like, I don't know, Jason, if you have a framework slide that we are discussing as a group.
I have the one in MCC one. Is that the one you're talking about?
Yeah, I mean, the one where we show the stack and,
Yeah.
where the debate started, right?
Sure, I have that here. Are you seeing the one MCC slide?
Yeah.
And then you were also looking at thinking
More
about
of this, right? Yeah. Which
Make it a
is
little bit bigger.
Yeah. So I think,
Like
in
that.
this, we've been trying to emphasize, right, these convergence around some open formats like Substrate, Arrow, and the PyTorch TensorFlow and JAX, Onyx, etc. So there is a lot of alignment of thoughts in terms of, can we converge and go into API definition sort of advancing beyond, the deficiency of work in both areas where they were too pure in one side or the other. So can we do a best of breed architecture? Like I would say that the CASD work was very pure on the fixed function side and really struggled to do a very pipelined, programmable flow between host and accelerator. And then the more programmable architectures, they struggled to deliver cost, power, and acceptability benefits because they just were imposing too much on top of what memory and storage are largely commodity markets, right? So customers want some attributes of the right side always. Okay, like in that diagram, they want some characteristics of that architecture to remain. So we could look to combine the best of both and justify why this box is the ticket to then doing the new architecture. Okay, I think scope limiting is a very good thing.
So I guess the biggest question I have is, well, first I should say I agree with the definition, the two different kinds of architecture between device first and accelerator first. Well, I think it would be nice to have one API that supports programming using both kinds of devices. I mean, this is the question: is it worth pursuing, or is it a splitting factor? If it is a market segmentation, why is it not two totally different, totally separate APIs?
Good question again. I think
just oil and water, and you don't have to worry ever about really mixing them. It's unlikely that they would be mixed.
Yeah, I mean, if you look at the AI supercomputers, they ended up engineering their own storage, for example. Okay, but I don't know whether that is continuing to be the intent of data center architects moving forward. So I do agree with you. There is a dichotomy that we could try to maintain, but I sense that that they are looking to converge and not end up with like too many bespoke components in the data center. So a lot of people are rejecting, like a few customers, large customers I've spoken to, they are rejecting co-packaging of memory and storage elements with the GPU, even interconnect elements with the GPU. And they're saying, no, while it is convenient for large vendors to sell us fully integrated systems, but we actually do want to keep them separate and connected using open components and take benefit from disaggregation and these kind of trends. So I see that, while it may be that you want to have different storage for different workloads, in the end, I think the world wants to converge. The cloud service provider world doesn't want to go there, I think, long term. And same thing for memory. I think that, yes, in packaged memory, they will agree. I think the moment you go to component memory or disaggregated memory, they're not looking for two architectures.
I guess some of this is devil's advocate. I think it might be possible to support both. I would certainly like to support both at the same time.
I think your work, right, the work you presented on Udon, it's kind of, shapes one end of this bounding box. And I think the CS API work that Samsung presented kind of actually all of you, right, presented that it shapes the other end of that box. So somewhere in between, and I am interested in leveraging the great work that was done in CN and VME to see if some of the needs, the more common needs of AI and database workloads that are pushing the frontier and requiring great flexibility, if we can meet 80–90% of the needs by embracing some of these high-level open formats, along with lowering compilers like Marvell have been describing. Okay, I think that sort of is the rough framing where this is trying to go, and lines up with one MCC, I think, right, Jason?
Yeah.
Because one MCC also is trying to address a couple of different kind of architectures with the same API. PIM and PNM, right?
Right. I see what you're saying. Yep.
So if the API that we have gets too close to PIM style, then it will have trouble with the other. It will be too integrated for the other use case.
So it sounds like one of the things we need to explore then is whether we believe that these two architectures can be merged or at least be handled together in a combined API or combined framework. And
Yeah.
if the answer is yes, then maybe that's the direction we want to go. That's what I'm hearing. I think that's probably my preference as well. But I think John kind of echoed that.
Yeah. Yeah, if it's possible, then
Right.
it probably should be done. And just an open question of where are the roadblocks, where are the real splitting concerns for a programming model? Where would that become impossible to support both?
One of the things I wanted in the programming model and the interface was accommodation of both message passing and shared memory. This is one of the reasons why I really like the idea of delivering all this into MPI first and going from there, because it's the most widely adopted library that has both abstractions in a reasonable way. So we've learned from the work we have seen presented to us that it has good implementations on top of both scale up and scale out architectures. So it doesn't stress people to say, hey, here are my components, here are the large pieces of memory I'm working with, and here's what I'm trying to do with them in terms of data movement and operations. And my bias is to extend that set of operations very slightly to accommodate some of the types that are emerging in the AI and database worlds, and to largely take that embraced and extended version of MPI and deliver it on top of the varieties of architectures that we are trying to comprehend here. I also, there's one fear I have. I mean, I sound like I have all the answers, but I actually worry about this a lot. That suppose none of us was able to do anything, okay? And in the software world, no problem ever gets unsolved for more than a few months, okay? So what would happen if, Samsung people, let's say one MCC people had no help from OCP? in a better API than what they could do on their own. Okay, they would do something like a PyPim. Okay, and then they will surface that Python interface and with some functions that execute really well in their fully integrated device with offering a service maybe on Ethernet. Okay, and then somebody else will come along and they will have another thing and it will have a different characteristic. It will be like, a farm of GPUs that does compute only. And it will offer some AI functions also over Ethernet. And so something like, data center Ethernet with RDMA and some of the UEC capabilities might emerge as a lingua franca that all kinds of things talk. And you would not need any of this that we are talking about. So that's the natural direction, which is more and more integration, and then protection of investment in the data center fiber, no rack level versus data center scale limitation because of optics that they're leveraging, and you're good to go, staying in the same architecture. The problem is that AI has already proved that level of integration does not work for it. So it will put a lot of pressure on data center fabrics if we went there. This is where I think that, some of what we talk about here, it creates a unit of scaling that that leaves, Ethernet to its proper use cases, not having to connect like PyPim devices on Ethernet. I think that would be not right.
All right, we probably should make that the last comment. Thank you, Pankaj. We're past the top of the hour, and some folks probably have to get on to their next meeting. But wonderful discussion, wonderful presentation. Thanks for the education,
Yeah.
and we will definitely continue next time.
So will
Thanks.
you send out an update then next week? It'll be normal schedule plus also a late night.
That is the plan, but Gaurav has to confirm the late night. But I will send a meeting invitation when we have that confirmed.
Okay.
But we'll have the regular meeting for sure.
All right.
Pankaj,
see
are you
you-
able to
see you then.
send these slides to be uploaded?
Yeah.
Okay,
I'll do that.
perfect.
Yeah.
All right. Thanks, everyone.
Yeah,
Bye.
thank you.